Hello friends, welcome to Engineering Simplified. Today we are going to learn about concepts and techniques related to design of RCC cantilever retaining wall. After watching this video, you will be able to find the load developed in each part of the retaining wall, and you can design an efficient RCC retaining wall. Before starting today's lecture, let us start it by a question. What is the main purpose or what is the aim of design from an engineer's point of view? Designing a structure means the design structure should be safe, it should be safe and should be economical. In case of RCC retaining wall, the safety means the structure should serve its purpose without failing throughout its intended period of service. Means if we are designing a structure for 50 years of lifespan, then within the 50 years it should serve its purpose. It shouldn't fail. Economical means the design should be most economical. Means it should be most cost effective. Our design should be most cost effective. We can make our structure more bulky. Bulky structure means it will be safer, but it will be not economical. But so that we should remember that our structure should be both safe and economical. Here safety in RCC retaining wall means it should be safe both externally and internally. External stability means the wall should be safe against overturning, sliding and bearing pressure. In last video, I have given a brief introduction about the external stability. Internal stability means the overturning means that the wall should not overturn by its toe. It should be safe so that it should not overturn by its toe. It should not slide. Means sufficient friction should be developed between the base of the retaining wall. If this is a retaining wall, if it is resting on the soil, then sufficient friction should be developed between the base of the retaining wall and the soil so that it should not slide by action of the horizontal force. The horizontal force is due to the action of active work pressure. It should be safe against bearing pressure. In the last video we have seen that there is a development of vertical pressure. It is developed in trapezoidal fashion. Then the maximum vertical pressure will be developed at toe region and minimum is developed at heel region. The maximum vertical bearing pressure should be less than the bearing capacity of the soil, and the minimum vertical pressure should not be tensile in nature. If it will be tensile, if it will be negative, then that means there is a loss of connection between soil and heel. We don't need that. So the design should be externally stable. Means it should not overturn, it should not slide, or should not fail by bearing pressure. Internal stability. Next we go to internal stability. In the structure, internal stability means the structure should be able to resist a flexure or bending and shear generated by the action of external forces. We know that due to any external force and internal resistance occurs. As we know, concrete is poured in tension. So, due to these external forces, if the tensile stress generated in concrete is not safe, then we provide reinforcement. So once we know the structure is externally stable, then we go for internal stability. Okay. So now we will go for different steps in design. Okay. What are the data required for designing? The first data we need is reduced level of ground level and the top level of soil retention. This is the ground level. Okay. This is the top level of soil retention. If we know this RL and this RL, we can find out the height difference. Okay. This data we need. Next data, we need different soil properties. We need the density of the soil, the angle of repose or the internal friction angle. We need safe bearing capacity of the soil. Safe bearing capacity means this is the maximum pressure soil can bear. Okay. This is the maximum bearing capacity means the maximum pressure soil can bear without failure. There are different methods for calculating the safe bearing capacity. You can find it in any standard geotechnical book. Then there is a coefficient of friction between soil and concrete structure. Okay. We know that the retaining wall is resting on soil. Okay. The angle of internal friction is high, and the coefficient of friction between soil and concrete structure is defined as delta. If we don't know the coefficient of angle of friction between soil and concrete, we can take a relationship that delta will be 2/3 of angle of internal friction. So coefficient of friction between the soil and concrete can be mu. We can take it as 10 of delta. Then we need the properties. We need the material properties. Means what materials we are using. Means grade of concrete. We need the concrete grade. Is it M20 or M25 or M30 or the steel grade. Means it is Fe415 or Fe500, or nowadays we are not using Fe250. So I am not telling it about. Now our next step is to proportioning of the retaining wall. Means we should first I have already told you that first we have to check the external stability. Before checking the external stability, initially we have to check some initial sizes of the retaining wall, means size of the stem, size of the slab, and we will check that it is externally stable or not. Once we will find out it is externally stable, then we will go for internal stability check. And if it is not internally stable, then we have to provide reinforcement. So first we have to find the depth of the foundation. It depends on the bearing capacity. Depth of the foundation is found out by using Rankine's formula. Okay. You can find out in any geotechnical books. Okay. Minimum depth of the foundation is equal to ratio of bearing capacity by density of the soil into 1 minus sin phi by 1 plus sin phi whole square. So here Q is the bearing capacity of the safe bearing capacity of soil. Gamma is the unit of weight of the soil. Phi, this phi is the angle of internal friction. Okay. We know I have already told you about that. We know this height. Okay. We already knew this height by subtracting the RL of this level and RL of this level. Now we found out the depth of foundation D. Then the overall depth of the wall will be summation of this depth and this depth. Okay. This is the overall depth of the foundation. Let it represent with capital H. Now, this is the basic proportioning. There are some. Initially we have to take some initial dimension. We have to check it if it is correct or not. If it is not satisfying the stability requirement, then we can change the initial dimension. Okay, so there is some empirical relationship to find the initial dimension. Okay, we can find out the base width, this base width of the slab by this formula. There are two types of shape of the retaining wall, L-shaped retaining wall and T-shaped retaining wall. This is the T-shaped retaining wall, this is the L-shaped retaining wall. For T and L-shaped retaining wall, there we can find out the base of the retaining wall, base width of the retaining wall by this formula. Here P is the active arc pressure. This is the active arc pressure. And gamma, this gamma is the unit weight of soil, not concrete. Okay. There is other formulas are also available. I will tell you later. Okay. And the toe width. What is the width of the toe region? We can generally assume the toe width will be greater than 0.33 times of width of the base slab. If this is the total width of the base slab is given as D, then the toe width will be greater than 0.33 times of width of the base slab. We can take more width of the toe width, but it will be more costlier. So we should assume a cost-effective toe width, so that it will the structure will be stable and it will be economical. The thickness of the base slab. If the overall height is capital H, then this base slab width we can take it as H by 15 to H by 12. You can take any value between this H by 15 to H by 12. If the base means this capital H height is 6 meter, this overall depth is 6 meter, then our thickness of the base slab will be between 6 by 15 to 6 by 12. Okay. We can assume higher value, but then we have to check for stability. We should always design so that our dimension will be minimum, so that less amount of concrete will be consumed and it will be economical, as well as it should be safe. So we are taking two concepts, that means safety and economy are both important for us. So it should be economical and it should be safety. We can make it more bulky, but it will be much costlier. Okay. Now we will go for design of stem. Generally, we initially take the width of the stem as the width of the base slab. Let the width of the base slab is bs. Then initially we will take this stem width is bs. And for the economical design, what we do, we take the stem as a tapered section, not a constant section. Means with height, its dimension decreases. Why we are taking this? We know that the earth pressure varies linearly, and it is maximum at it increases with depth. Okay. So at top, the force or the moment generated due to the earth pressure will be lesser as compared to the force and moment generated at much greater depth. So the dimensions at top level will be lesser than at bottom level. So then our structure will be much more economical. Okay. So initially we are taking the stem width as the edge of the base slab width. Okay. Now when we design the stem, we will consider it as a fixed beam, and it is fixed at this connection point between the slab and stem, and we will design it as a slab. Okay. As we know, the retaining wall extends in three-dimensionally in this fashion. Okay. So we have studied how to design a one-way slab. While designing a one-way slab, we design it as a beam of 1000 mm or 1 meter width of beam while we design a slab. Likewise, we will take a unit width, means 1 meter length, and design it as a slab. So the slab is fixed at a point, and the active of pressure is acting like this fashion. At bottom it is Ka gamma H. Then the bending moment diagram will be look like this: Ka gamma H cube by 6 at this joint point, or at this connection point between the stem and the slab. Based on the maximum bending moment, this is the maximum bending moment value Ka gamma H cube by 6. Depending on the maximum bending moment, we are designing the stem. Okay. H, due to the load, the stem will bend like this. Okay. So tension will develop in this region. So we are going to give tension reinforcement in vertical direction in the inner face. Okay, this is the main reinforcement. So how we will calculate the main reinforcement? Before calculating the main reinforcement, first we have to know what is the maximum bending moment. The maximum bending moment developed with Ka gamma H by 6. So for designing, we will take the design bending moment will be 1.5 times of maximum bending moment. Okay, we will design based upon this. Then we will take this design bending moment, and first of all we will find out that the initial depth, means the initial base width, initial stem width what we have taken, is it correct or it needs to be changed. So how can we find out the stem width? Okay. For a balanced section, we know that grade of concrete and grade of steel. For this grade of concrete and this grade of steel and this movement, what should be the balanced depth? We can find out. Okay. If the stem width initially we are taking, the stem width initially we are taking is the overall depth. Overall depth is the summation of effective depth plus clear cover plus half of the reinforcement depth. As we know that this is a beam. Okay, these are the reinforcement. The overall depth is top to bottom depth. Okay, the effective depth is from top to centroid of the reinforcement, and this portion is the summation of clear cover, and if the reinforcement have a diameter 5, then 5 by 2. Okay. So here, in case of retaining wall, as it is always in contact of soil and water, the clear cover should be always be greater than 40 mm. Okay, remember this. The clear cover for retaining wall is always greater than 40 mm. Okay. Now, when we check that the balance, the D we have taken the effective depth. No, I am not telling about the overall depth. I am telling about effective depth. If the effective depth is greater than balance depth found out from the equation. Okay, then the depth we have taken initially by considering the stem width equal to base slab thickness is correct. We don't need any change. Okay. Now we have to find out the area of the steel. Okay. We can use an equation from IS code in clause number G1.1 G1.1D. Okay, it is given in page number 96 of IS 456/2000. Okay, in annexure G. Okay. The equation for MU equal to 0.87 Fy AST D 1 minus AST Fy by DDFCK. Okay. Here, what are the data given? Fy is the grade of steel, AST of the area of the steel needed. This data we need to find out. AST effective depth we found out previously. If it is greater than the balance depth, then what we have taken the effective depth, it is a correct. Okay, grade of steel. And what is the B width? We are considering the unit width of the slab. Means it is like a beam. Consider a beam having width of 1000 mm, means 1 meter, and depth. This is the overall depth, and if it is a reinforcement, then this is the effective depth from top to center of the reinforcement. From this equation, this is what when we will put the value of mu, this value of mu, I have already told you, we found out it is a multiplication of 1.5 times the maximum bending moment. That it will be at the connection point between the stem and slab. Okay. From this, we will find out the area of steel needed. From the area of steel needed, we can find out the spacing of the steel bar needed. If we are taking a 16 mm dia bar or any 5 mm dia bar, then the spacing of the bar we can find out is equal to, it will be spaced in 1000 mm width, so 1000 into pi by 4 into pi square divided by AST. Okay, so this will be the main reinforcement which will preliminarily resist the flexural stress. Okay, we can curtail every, I have told you, and you have seen in the picture, the bending moment is decreasing. So we are designing for maximum bending moment. We are giving the steel for maximum bending moment. So we don't need to put the steel everywhere the same amount of steel. So at certain height, at h by 3 height, we can calculate the bending moment here, and we can curtail the amount of steel coming up to this point. And likewise, at a height of 2h by 3, we can calculate the bending moment here, and we can curtail the remaining portion. Okay. This is the diagram of main reinforcement. Okay, main reinforcement. And with the main reinforcement, we have to give the distribution reinforcement. Here we are giving the minimum distribution reinforcement. The minimum distribution reinforcement. What is the minimum? What is the area of the minimum distribution reinforcement? We are using the clause number 26.5.2.1 of IS 456/2000. Here, the minimum reinforcement distribution reinforcement value is 0.12% of total cross section area of the beam. Means here the total cross section area equal to B into D. So 0.12% equal to 0.0012 into B into D. Here D is total overall depth. Means it will be summation of effective depth plus effective depth plus clear cover cross having D. Okay. This is the distribution reinforcement which is perpendicular to the plane. Okay. Now after we found out the stem width, now we will do a stability check. It is better to do the stability check in the tabular form. Here we will write the load of different points, different parts. Means we can divide slab into one part, this slab into one part, this stem into another part, and the soil over the hill region is another part, and the soil above the toe region is another part. And for these different members, we can find out the load. As you know, its density, its dimension, we can find out its load, and how much distance its centroid is from the toe. This is the toe. From the toe, the distance of the centroid we can take it, and the multiplication of the distance with load will be moment, and the sign of moment. Here we are taking anti-clockwise movement as positive, and clockwise movement as a positive and anti-clockwise movement as negative. As here, in this picture, anti-clockwise movement will try to overturn this retaining wall by its toe. Okay. And we will do the stability check. After the stability check, we can draw the bearing pressure distribution below the slab or below the foundation. In the last video, I have told detail about this. From this, we can find out, we can note that what is the maximum bearing pressure and what is the minimum bearing pressure and how it is distributed. It is distributed in trapezoidal fashion. Now we will go for design of heel and toe slab. First, let us consider the heel slab. Okay, this is the heel slab. When we will design, we will consider it as a fixed beam. It is fixed in this portion. So, what are the loads acting on this heel slab? The overburden of the soil will be one load, and the self weight of the concrete will be another load, and the upward oblique bearing pressure. It is acting in trapezoidal form. Okay, this upward direction bearing pressure. So this will be written over here. The downward direction, the loads are self weight and weight of soil, and upward direction loads are the oblique pressure of soil. Okay. Generally, the downward force here is more than upward force. So the heel will bend in this fashion. So tension will develop in the up direction and compression will be developed in bottom direction. So we are providing tension enforcement in this fashion in the toe slab, and we are calculating the in this heel slab. So we are calculating the amount of reinforcement in heel slab by the equation I have previously given you. That is the mu equal to 0.87 Fy ASTD into 1 minus AST Fy divided by BD FCK. That is the clause G 1.1b. Okay. From this we will find out the main reinforcement area. While designing as a beam, we are considering it as a unit beam. This width is 1000. We know the thickness of the base slab. Okay. We can design it, and we are giving the distribution reinforcement H 0.0012 into D into D. This is the distribution reinforcement value, distribution reinforcement area. Now we are going to the design of toe. In the toe region, what are the forces acting? The soil over the toe will give a downward force. The self-weight of the concrete will give a downward force, and the absolute pressure, it is in this region, will give a upward force. In generally here the absolute means upward force will be greater than downward force, so the toe will deflect like this. If this in this region means the bottom region tension will be developed, and in the top region compression will be developed. So in the toe region we are giving main reinforcement in bottom portion. Okay. This is the diagram. After giving the reinforcement, we will check for shear. Generally, we are checking if the base slab, the same effective depth is D. We are calculating the shear stress developed at this D distance from top from the bottom. Generally, we don't need any shear reinforcement, but if you need, you can give minimum shear reinforcement.